Hi, I'm back again, and we're going to continue our discussion of iteration as it relates to JavaScript. And in this lecture, I'll begin by solving a new problem being testing to see whether an integer is a prime number. And I will implement a solution using a for loop, and we'll look at, how that process, how that algorithm works. And what we'll discover is that the problem can be solved with that, familiar looping structure, but there are some problems doing it that way. That the algorithm based upon my using a for loop is going to be somewhat inefficient, and then I'm going to, at that point, introduce the while loop and try to convince you that some problems are best solved with a for loop, other problems are best solved with a while loop. So, to get things started, I have put together a quick example here in Microsoft Word showing what a prime number is and how we can go about testing for it. And the algorithm that I'm going to describe is not terribly efficient, but nevertheless it's very simple. So it's going to allow you to, understand things, understand what we're doing very rapidly. And then we'll make some adjustments to this algorithm as we look at a second program example. So what is a prime number? Prime number is any number any integer number greater than 1 that is only evenly divisible by 1 and itself. Okay, so think about that. It's a integer, meaning a whole number, and it has to be an integer value greater than 1, and it can only be divided evenly by 1 and itself. Okay, so that said, let's look at a couple of concrete examples, one of which is a prime number, the other is not. Okay, so we're going to consider an integer value of 7. Okay, so that is an integer value greater than 1. And it so happens that's an odd number, but that's not really, anything important here. The fact that it's odd is of no consequence, really. So what am I going to do? I'm going to test to see whether this thing is a prime number by repeatedly dividing it by numbers in the range of 2 through the number itself minus 1. So in this case, I'm going to be dividing by numbers in the range of 2 through 6. N minus 1, 7 being n minus 1 would be 6, right? So if I, at step 1, divide my number n by 2, I get a remainder of 1. Now I'm not concerned about the quotient, I'm just interested in the integer remainder here. So, think back 3rd grade, if you divide 7, if you divide 7 by 2, you're going to get an integer quotient of 3, and you're going to get an integer remainder of 1. If you divide another time, a second time, by the next number in the range, which would be 3, if I divide 3 into 7, I get an integer quotient of 2 and a remainder of 1. And if I divide by 4, I get a quotient of 1 and a remainder of 3. If I divide by 5, I get a quotient of 1 and a remainder of 2. And if I divide by 6, I get a quotient of 1 and a remainder of 1. So in the range of 2 through n minus 1, I do repeated division and examine the result of the division, specifically the remainder value that results. And what I find is that nowhere along the way did it divide evenly, therefore 7 is a prime number. Take another example, an example of yet another odd number, but again that is of no real consequence here. It is it's going to turn out that 9 is a non-prime. Okay, so if I divide by values in the range of 2 through n minus 1, I'm going to be dividing by 2, then 3, then 4, then 5, then 6, then 7, then 8. Okay, so 9 being n minus 1 would be 8. And the first time I divide, I get a remainder of 1. The second time I divide, and I have this highlighted in red for a reason, I divide 3 into 9, I get a quotient of 3 and a integer remainder of 0. Okay, so at that point, I've discovered that that 9 is not a prime number. However, if I follow this algorithm, and continue to divide by numbers in the range of 2 through n minus 1, then I maybe store away that fact, but I continue on needlessly and divide by 4 and get a remainder of 1, divide by 5, get a remainder of 4, and so forth. So I'll end up having to do 1, 2, 3, 4, 5 needless iterations, 5 needless arithmetic operations. So for a computer to have to do 5 needless operations like that, no big deal. But if the value of n was something much, much larger than 9, at some point this algorithm is not going to scale very well, and I'm going to see that there's a degradation in performance, and what I really need is to revise the algorithm so that it's more efficient. If I can revise this algorithm at some point so it can, stop immediately when it discovers a remainder value of 0, then I'm going to make it a whole lot more efficient. And I'll demonstrate that that can be done here as the lecture continues on. But for now, this is the basic algorithm. What I'm going to do is just set things up so that it will repeatedly, therefore, iterations involved, but it's going to repeatedly perform this arithmetic operation for every possible division in the range of 2 through n minus 1. Okay, so let's look at the program code where I implement that kind of thing. And should have had this open. I'm going to do prime test 2. Okay, oops, wrong way to open it here. Try that again. Prime test 2. I'm going to open with my browser, run the program, and let's try those two numbers, okay? So the first number I'm going to test is 7. I test for prime, and it turns out that it tells me it's a prime. Now I should have output to this box, but you know how to do that, and just we're going to live with the alert statement. I'll reset. Looks like I need to fix that reset button too. Okay, well, I'm going to try it with 9. Okay, test for prime, and 9 is not a prime. So again, 7 turns out to be a prime, and 9 turns out to be a non-prime. Okay, so if you're familiar with prime numbers, you probably understand that 19 would be a prime number, and that 17 would be a prime number. I'm just going to throw a few more prime numbers out there so you can see that 11 would be a prime number. Great. I'm sitting outside in my gazebo recording this, and there are 2 cats in my yard, neither of which belong to me, that are having a big fight. Sorry about the distraction. Okay, so let's try, I don't know, 4. Okay, so 4 is not a prime. I'm going to do one more. Okay, let's try 2. and 2 is out of range. Okay, so I have this program set up so if I attempt to divide by, if I attempt to test 2, it just tells me it's out of range, because again, the rule for determining whether a number is a prime or not is whether a number can be evenly divided, within the range of 2 through n minus 1. And in the case of 2, if I begin dividing by 2, well, any number divided by itself is going to divide evenly. So 2 is kind of the exception case here. 3, on the other hand, should work fine. Okay, so 3 is a prime. All right, so I've messed around with that enough. Let's take a look at the actual program code. And if I look at the way things are set up, then I have a function called prime num, and I'm passing input from my form to this parameter called mynum. Okay, so mynum would correspond with, in my previous examples there, the value of n. So you can think of mynum and n being the same thing. And I declare a variable up here. We'll see why that's done here in a moment. I also declare a variable called flag, okay, and as I make decisions along the way, then flag is going to change if I discover there is a non-prime. Okay, so starting out, I'm going to check to see if mynum is greater than 2. And again, because 2 is the exception case, if that's not true, it's going to take the else path down here and fire off an alert that says out of range. We saw that demonstrated, so that's where that's happening. Assuming that the input parameter value is greater than 2, then we drop into a loop, and that loop is going to be set up to iterate starting at 2, and it is going to iterate until I reaches a value that is, it will continue to iterate until I reaches a value that's equal to mynum. Okay, as soon as I gets bumped up to a value that's equal to mynum, it kicks out. And that's going to allow me to iterate with I having a value that starts at 2 and ends at a value n minus 1. That's the range I needed to divide by. So as I progress through the for loop, I'm going to divide my input value by I, and I'm going to divide using a special operator, the %, which performs modulus division. Okay, so what is modulus division? Modulus division is a special type of division that is supported by most programming languages, whereby integer division is performed and the quotient is ignored and the integer remainder is stored away into some other variable. So in this case, by way of an assignment statement, I'm going to divide mynum, let's say that value is 7. Okay, I would divide 7 by 2, and I'd get an integer quotient of 3, and I would have an integer remainder of 1, and the integer remainder of 1 would get stored away in my rim. Okay, so this seems a little strange, but if you think back, third grade arithmetic, when you were first learning how to divide what used to be called short division, I don't know what it's called now, integer division, there are two parts that result in doing the division. You have the quotient as one component, you have the remainder as a separate component. And when we do modulus division, it ignores the quotient component and only stores away the integer remainder that results. So in this case, I would check and find that rem is equal to 1. 1 would be, the value stored in rem. So when the if statement is executed, it checks to see whether or not 1 is equal to 0, and in this case it would fail, and consequently flag would remain 0. And then we go back through the loop a second time where I would be incremented by 1. Its value would change from 2 to 3, and I would be dividing, if 7 is my input parameter value, I would be dividing 7 by 3, and I would get a quotient of 2 and a remainder of 1 again, and store the 1 in my rem, and then it would fail the if test, and it would continue on in that fashion, and it would continue to fail this if test, and by the time it completed the for loop, when we get to this point right here, once it ends the for loop, flag would still be equal to 0. And if I reach this point after doing those repeated divisions in the range of 2 through n minus 1, if I get to this point and flag still has its initial stored value of 0, then it would take the if path and fire off prime. Otherwise, if it ever divided evenly in here, even once, it would get into this if statement. It would change the value in flag from 0 to 1, at which point it would take the else path. This is a two-way decision structure here. It would take the else path and fire off a alert that says not prime. Okay, so let me real quickly then just kind of refresh. I'm keeping track of my remainder, and I am using another variable to signal once I've performed all the divisions that are necessary to signal whether or not I ever divided evenly. And again, it's sort of the strategy here of innocent until proven guilty, right? So I'm going to declare this thing to be a prime number, but if I ever divide evenly, then I will declare it not a prime number, but a non-prime. Once I go through all the required divisions, I test to see what's in flag. It's either going to tell me with a value of 0 that it's prime, or it's going to tell me that it's not prime, because it will have been changed from its initial value of 0 to 1 here. The overall flow of control is that I have an all-encompassing if-else statement, and that all-encompassing if-else statement is going to check to see whether the input value is within a range where a test for a prime number would be appropriate. So if it's a value that is not greater than 2, there's no need to test for it. If it is a value greater than 2, then it will take the if path and do everything that I have highlighted. Namely, it will go through this looping process 2 through n minus 1 times. Every iteration of the loop, it divides by the next value, and it checks to see whether the resulting integer division produces a 0 remainder. And if it does, it's going to set this value so that I can recognize later on that I'm dealing with a non-prime number. Otherwise, if the division results in a non-zero value, this if statement, which again gets executed with every iteration, is ignored. That's a one-way decision inside of this for loop, which is inside of an overall two-way if-else statement. Once I complete the for loop, still within this overall if path right here. Once I complete the for loop, I have a nested, completely separate, nested two-way decision. I check to see one way whether it's prime, and I check to see whether it's prime, and then I have one path that will provide output indicating that it's prime, or if it takes the alternate path, I have output that will indicate that it's not prime. Okay, hopefully that makes sense, and that's the nature of the first program, and it is based on the algorithm that I show you here. And if I put in a value of 9, it's going to go through all these steps, and if we could crawl inside the computer and see what's going on in these memory locations that are referenced by different variables, we would discover that along the way the remainder is 0. But the program isn't smart enough to recognize that. So what could we do to fix the problem? Well, the way we can fix the problem is to use some kind of loop structure that doesn't, continue on like the Energizer Rabbit, something that will stop early on. Now, the for loop is a fixed iteration loop structure, meaning that it's going to iterate a fixed number of times. That fixed number of times is going to be based upon that expression right there. It's going to iterate so long as that thing evaluates true, and it's going to bump it up in this case by 1 each time. Okay? So it's going to iterate. We know in advance how many times we want to go through this. It's going to iterate a fixed number of times. There is another loop structure called the while loop. And let's take a look at a program that uses it. Okay, so I'm going to close this up. And that program is Prime Test 3. And I will open this with Firefox, and I'll put in a value of 7 and test for prime, and it tells me it's a prime. I'll put in a value of 9 and test, and it tells me it's not prime. And trust me on this, I could continue to put other numbers in, and we would, find that it's testing properly. Now, how is it different than the previous example? If I look at page source, I have a function, okay, called prime num. I pass it a value to this parameter called my num, which acts like in my previous explanation. Then I reach deep into my bag of tricks, and I am going to take into consideration some obscure mathematical rule that says that when I test for a prime number, I don't really have to test all the way out to n minus 1, that I can actually test, I can shorten the number of tests that I perform. I only need to divide by a number that the maximum number I need to divide by is a number that is the square root of n. So in JavaScript, there is a built-in math object, and it has a built-in square root method, and it is designed to perform the calculation to find the square root of a number. And so I find the square root of my num, and that really is as far as I ever need to divide. So I'm going to immediately be able to shorten that, the number of times that I have to divide. Instead of always dividing clear out to n minus 1, I'm going to shorten that considerably, and I will only divide to not n minus 1, but to the square root of n times. So I store that number away. I call it square root my num. I create a variable called I as a local variable, and I set it equal to 2. Okay, so that's the beginning. So square root of my num represents the upper limit on the number of times I need to divide, and I is going to represent initially the lower limit on the number that I should divide by. Then it's going to get incremented by 1, and eventually I'm going to have this thing set up so that the maximum number of times that I divide will be, for the range of numbers, 2 through the square root of n. But it gets better than that even. Okay, so I declare this variable called myRem, which I'll use here in a moment. I have this variable called flag. It's going to be used for the same purpose. It just sits there and monitors whether or not I divide evenly, and if I do divide evenly, then its value will be switched from 0 to 1. Then I have a overall if-else structure, okay, and we saw this before. This is where I check to see on the if path if the parameter value is within a range that I can test for a prime number. So if it's greater than 2, I can test for a prime number. It's going to do a whole bunch of stuff, and that whole bunch of stuff is outlined right there, is highlighted right there. But in the event that that if statement fails, it will take the else path and simply say out of range. Okay? So everything is wrapped up into this all-encompassing two-way decision structure. And should I discover at this point that I have a number that I can test for a prime number, then it proceeds down the if path, and the first thing we encounter is a flow of control structure that performs looping, and that flow of control structure is right here. It is a while loop. Now, how does a while loop work? Well, while loop works very, very much like a for loop. It begins with the keyword while. It's a pre-test loop structure, but it is not a fixed iteration loop structure. In other words, once I start in this while loop, it's going to continue until it discovers that it needs to stop. And under some circumstances, it might iterate 10 times. Another time when I run the program with different data, it might iterate 5 times. It will determine how many times it needs to iterate. So how does that work? Well, following the keyword while, I have an expression, and when that expression evaluates true, the code that makes up the block in the while loop will execute. When that expression evaluates false, the code that makes up the block in the while loop is ignored, and program control will pass to the statement immediately following the end of that block, and in this case that would be right here. Now, what happens is, somewhere in this block of code itself must monitor what's going on and change this expression when it's time to stop looping. Now, a while loop is really a universal loop structure. I can always use a while loop in place of a for loop, but I can't always use a for loop in place of a while loop. A while loop is a universal loop structure. I can make a while loop behave just like a for loop. But under circumstances where I know in advance how many times I need to iterate, where I need a fixed iteration loop structure, a for loop is a much safer loop structure to use. The problem with the while is that I have to build into this thing some mechanism to shut it down. Otherwise, I create what's called an infinite loop. And for most purposes, an infinite loop is a bad thing to have in a program. An infinite loop is what it sounds like, a loop that never stops. If I don't design this loop properly, then it will run forever and the program will hang, and that becomes the source of, a logic error, potentially. Now, infinite loops are almost always bad things. I suppose if I were, designing a cruise missile or something, and I wanted it to monitor the elevation at which it's flying and be able to stay at a constant elevation above the ground, and I want it to constantly look left and right and make sure it doesn't run into any buildings, and if it sees a building, fly around it. And I know that eventually, and it needs to constantly do that within a time frame. Maybe I put all that code inside of a loop and it continues to look up and down, left and right, up and down, left and right, and, do all the things that a good cruise missile should do. And I know that at some point in time, it's going to find its target area and destruct. Then, maybe I'd wrap everything up in a while loop. But unless I'm designing cruise missiles, let's say, I probably want to be real careful of infinite loops. Okay, so a hazard of a while loop is that you have the ability to write this code incorrectly, and then the program would just hang in that loop forever. All right, so in this specific case, what do I want? Well, there are two things that I want to check for, and they become the conditions by which I will either loop or not loop. So one condition is that I start I at 2, and after the second iteration I want it to become 3, and after the third iteration, let me try it again. I start I at 2, and after the first iteration it becomes 3, and after the second iteration it becomes 4. Okay, so I is going to continue to get bumped up by 1 with each iteration. It's going to be initialized to 2 and get bumped up by 1 with each iteration. And I've already said that I'm going to, use this obscure mathematical rule and only make my upper limit, or the maximum number of times I need to iterate, not n minus 1, but rather the square root of n. So long as I is less than or equal to the square root of n, that would be one condition for which I would like to make this loop operate. Another condition is where flag is equal to 0. Okay? So looking at it from the other standpoint, if it fails this test, that means I have divided the maximum number of times I'm ready to get out. If it fails this test, it means that even if I haven't divided the maximum number of times possible, then I still need to get out, because I have discovered early on that I have a prime number. So if I had this loop set up instead of the way the loop was set up with a for loop in the previous example, the while loop during the second iteration would discover that there was a division that occurred and it produced a 0 remainder, and would end after the second iteration, and it would save me 5 needless divisions along the way. Okay, and it would discover that because once it divided and got a 0 remainder, flag would get set to 0 right here, flag would get set to 1 right here, and then when it comes back on what would potentially be the third iteration, it would discover that flag equals 0 is false. That would get it out as well. So I have two conditions that can, control whether I loop or not. The condition I less than equal square root of my num, or flag equal 0. Either one of those conditions can influence whether this loop occurs because I'm performing a compound conditional test using logical operator AND that we looked at before. When I use logical operator AND, the most restrictive of the two operators, AND and OR, that means that the only way this overall expression right here evaluates true is when expression 1 evaluates true, when expression 2 evaluates true as well. True, true gives me a true and an AND truth table, and true, false, false, true, false, false give me a false in an ANDed truth table. So there we have it. I have substituted that for loop for a while loop, and that's going to cut down on the number of iterations considerably. You know, that alone will reduce it, and this also gives me the ability to sense early on if I ever divide by I, some value in I, and get a 0 remainder. Okay. Otherwise, now this is going to work the same way. It goes through the loop. The looping will be reduced considerably, and then eventually it falls out of the loop, and the same as before. So in this overall if path here, it will encounter, after this loop structure, it will encounter a completely separate two-way decision structure. So that control structure is following the first one in sequence, and it checks to see whether or not it should fire a message prime or whether it should fire a message not prime. And there we have it, a case to be made where if I use a while loop, it's going to allow me to get out of this much faster. And while that may not be a big deal for small integer values, again, if I start looking at extremely large numbers, and I think you can see it from the example where I checked to see whether 9 was a prime number or not, when I start dealing with values for n that are extremely large, then there is the potential to detect the fact that it is not a prime number early on, but have to continue on looping and making decisions and burning CPU cycles needlessly because I'm using a for loop and I'm having to deal with something that is going to execute a fixed number of times, whereas the while loop allows me to iterate a variable number of times. Okay, in the next lecture, I'm going to demonstrate another real-world problem and then make your project assignment.